Today we're covering IP addressing. Specifically, I'm continuing on with my last week's discussion, and today I'm talking about CIDR versus classful addressing and helping people understand the terminologies of classful and how that applies to modern day IP version 4 addressing. In order to do this, I'm going to share an application on my computer. Which hopefully you can see now. And so we're going to go ahead and get started with that. So I want to talk about, you should be able to see it now. It might take a minute to load. I'll just give it a minute to do that. We'll go ahead and get started, and hopefully this will do okay. So first off, there's this concept in IP version 4 addressing called classful. And when IP version 4 first came out, they divided IP addressing into classful schemes. They basically created what they called small, medium, and large networks. The reason they did this is because they really had no concept of what IP version 4 would become. It was intended to be used for a communication protocol between research agencies and military organizations. They had no idea that it would become what it is today. IP was responsible for a couple of requirements. Number one, it had to uniquely identify. So it had to identify hosts. So hosts on the network had to have their own unique identifiable address. And then secondly, it had to be able to have a way to route, meaning to get the communication from one point to another point. So they had an IP address and they had to figure out how to do that. So as we talked about last week, if you have an IP address such as 10.1.1.1, if this was your IP address, there must be a way to delineate in this address right here which portion of this address belongs to the subnet or network and which portion of this address belongs to the host. So there had to be a way to differentiate so that we would know which in this address right here, in this address, which part of this address took care of identifying the host and which part of this address was responsible for routing to that host. So that's what they had to come up with. So if a packet were to go across the network, on the header, on the IP header of the packet would be the address would be listed in here. A router device would read or inspect that packet. And as that packet went through, the router would have to make decisions. And it made that decisions by consulting a routing table. So it had to be able to look at this address and determine what is the network ID or what is the subnet ID. So it did that in a very simple fashion. And I'm going to now explain what that is. First off, we have to know that IP addresses can be converted to binary. So if I took this 10.1.1.1 address and I converted it to binary, then we would have an address that looked like this: 0, 0, 0, 0, 1, 0, 1, 0. That would be the IP address 10. That would be the binary equivalent of the dotted decimal number 10. And then we'd have 0, 0, 0, 0. That would be 1, and then we would just repeat. So this is the binary equivalent of 10.1.1. So that's 10.1.1. So the router, this routing device right here, the router, would inspect this destination IP and be able to make a decision. So what it would do is if it would look at these first few bits. If the first bit right here, the first bit, if the first bit is set to 0, then it considered this a Class A network. Or what is considered large. Okay, and that's basically how it rolled. And so basically, what networks would then be in the Class A scheme? Well, it's pretty easy to figure out. We take our first octet, and if the first one always had to be 0, well, the first possible number would be 0. And then if we were to take and then we could then maybe consider the next one, which would be 1. And then we could continue going, and we could figure out all the possible combinations, right? So as it turns out, the last possible combination would be when all these are set to 1s. And that is 127. So Class A networks were from 0 to 127. Okay? So that's basically how that worked. So then Class B networks or the medium networks. Oh, and by the way, before I get into that, in a Class A network, if I were to look at each of these octets if I were to look at each of these, this is the X octet. Oh, actually, let me make that the W octet. If this is the W octet, and then the remaining octets are W.X.Y.Z. In the Class A scheme, they said W is equal to the network portion of the address. Remember how I told you that the IP address had to do two things. It had to identify the host and identify the route or the network. So in this case, Class A, the W, this portion right here, was considered the network. X.Y.Z was considered the host portion. So in my example of 10.1.1.1, 10.0.0.0 was the subnet. Actually, I won't use the word subnet just yet. We'll use the word network. So this was the network ID. .1.1.1 was considered the host ID. Okay? So that's how they figured that out. And basically there's two rules you had to know. When all the host bits are set to 0, that's the network ID. And so one other address, 10.255.255.255, this was considered the broadcast ID. And that's when all the host bits are set to 1s. So this would have been that particular network, this large network called the Class A 10 network. So in a medium-sized network or a Class B, the first octet was, if it was set to 1, 0, the first two octets were set to 1, the first two bits in the first octet was set to 1, 0. So the question became then, if it was set to 10, just like I showed you here. So if it was set to 10, this was considered the. Oh, I'm sorry, I wrote that a little too low there. If the first 2 bits were set to 10, this was considered the Class B network. And if we were to sit and do the same thing we did with the Class A scenario, if we were to do the same thing we did with the Class A scenario, 10 followed by 6 zeros, that would be the first possible network, which is 128. And we could figure out all the combinations that go in between there, but the last possible combination would be 10111111. And so we would have to figure out what that is, right? And that's pretty easy to do. But just in case I don't want you to get lost, let's open up a calculator. And we can go ahead and go to binary mode on this calculator, and I can put in a 10111. Yeah, the screen redraw is really slow. I don't think I can avoid that. It's been happening this last couple of times I've been doing it. So in this case, 10 followed by 6 ones would be 191. So the Class B network range was 128 through 191. Yeah, that's I'm looking at it from another machine, and the screen redraw is really miserable. It's too bad. So anyway, the Class B network is 101111, and that's 191. So that's how you calculate to a Class B network. And so 128 through 191 was that. So Class C networks were when the first few bits were set to 110. So we could do the same thing. That would be the Class C network. And that would be 110 followed by 0 and 4 zeros. So that was 192. And then everything in between, 110 with everything set to ones, that would be 223. 223, I think, yeah. So 223. So Class C was 192 through 223. So that's how they figured out Class A, Class B, and Class C networks. All right, so that's how classful addressing scheme worked out. So this is how they determined the network. So let me just show you then how they knew what the network is versus what the host was. So as I told you before, if W was the network in Class B, W.X was the network, and Y.Z was the host. In a Class C, W.X.Y was the network, and Z was the host. So that's how they determine it. So if I had an address like 172 10.22.22.10, I would know that this was a class B because it fell into this range. And I would know that this portion would be the host portion because that's what the class B designated. However, CIDR does this differently. So let's describe what that is like. CIDR doesn't do that. It introduced this concept called a subnet mask. And what happens with a subnet mask, instead of using the first few bits, if you have an address like 10.1.1.1, you would get a second 32-bit address called a subnet mask. Like this. And then using the process of ANDing, you AND the IP with the mask and you get the result. And I showed you how to AND last time I did this. But 10.1.1, when ANDed with 255.0.0.0, is the network ID 10.0.0.0. So we no longer look at the first few bits of the address. We now use the subnet mask to determine the destination network. So this is the primary difference between CIDR and classful schemes. Now, for backwards compatibility, any network labeled through 0 through 127, except we don't really use 0 and we don't really use 127 for reasons I'll talk about later. But 0 through 127 was given a default mask of 255.0.0.0 or what is referred to as a /8. Now, why is it called /8? Because the binary equivalent of this address is 1, 2, 3, 4, 5, 6, 7, 8, followed by 24 zeros. So this is called a /8 because there's 8 contiguous ones in the mask. A class B, right, which was 128 through that 191, was given a default mask of 255.255.0.0 or a /16. And class C's were given the 255.255.255.0 or what we refer to as a /24. All right, so there you go. That is the primary difference between CIDR and classful schemes. And basically how they determine what the network ID is. And that is the primary difference between the two protocols. I mean, the two different methods of implementing the IP version 4 protocol. Putting it online.